In the previous lecture we were discussing about the momentum integral equation. In this lecture we will see that how this equation can be applied to calculate various engineering parameters. So, momentum integral equation So, now let us say that u by u infinity is a cubic polynomial. Okay. This is an approximate form. Now we have to obtain these coefficients a0, a1, a2, a3 from the known matching conditions. So we will write the conditions according to priority, because had we considered a linear polynomial, that is a straight line, then only a0 and a1 had to be determined. So only two conditions would be required. So question is which two conditions we will use. So we will write the most prioritized boundary conditions. So the first two boundary conditions that must be satisfied is that at y is equal to 0, u is equal to 0, this is no slip. Second is at y tends to infinity, u will be or at y tends to infinity is physically replaced by y equal to delta, because at delta velocity becomes 99% of u infinity. So this will be u equal to u infinity. So this is the boundary condition of our velocity at y is equal to delta. Then the third is at y is equal to delta, this one. These three are very obvious. Here 4 coefficients are there, so you require a fourth one. Can you tell what is the fourth one? So for getting the fourth one, we should appeal to the boundary layer equation at the wall. So at the wall, u is 0 at wall, v is 0 at wall, therefore this must be 0 at wall. So at y is equal to 0, okay. So with these conditions you can calculate a0, a1, a2 and a3. So let us substitute this and I will tell you the final answer with which we can proceed. This is very trivial algebra. So, at y is equal to 0, u equal to 0, that means A0 is equal to 0. At y is equal to delta, u is equal to u infinity, that means A0 plus A1 plus A2 plus A3. At y is equal to delta, del u del y is equal to 0. So, let us calculate what is del u del y is u infinity A1 by delta plus 2 A2 y by delta square plus 3 A3 y square by delta cube. So, at y is equal to delta, del u del y is equal to 0, right. So, at y is equal to delta, if del u del y is equal to 0, that means you will get 0 is equal to A1 plus 2A2 plus 3A3, and at y is equal to 0, del 2u del y2 equal to 0. So, del 2u del y2 so that means 0 is equal to A2. So, A0 and A2 are 0. So, let us make those 0 here. This one also. So, A1 plus A3 is 1 and A1 is minus 3A3. So, minus 3A3 plus A3 is equal to 1. So, A3 is minus half and A1 is equal to 3 by 2. So, the velocity profile becomes u by u infinity is equal to 3 by 2 y by delta minus half y by delta cube. So, we will substitute that here. Then I will just outline the method of integration, because this is just a polynomial integration, there is no big trick in this. All of you can do this, but I mean there are good systematic ways of doing it, like you assume y by delta is equal to eta, then you have dy is equal to delta d eta. So, what is tau wall? So, del u del y is del u del y at y is equal to 0 is 3 by 2 delta. So, this becomes 3 by 2 delta rho u infinity square is equal to d delta dx. This delta will come out of the integral, this will become 0 to 1 3 by 2 eta minus half eta cube into 1 minus 3 by 2 eta plus half eta cube d eta. Left side there is a u infinity, right. So, this is, yeah, there is a mu also. So, this is just multiplied by u infinity. So, there is a u infinity and there is a mu. So, this is del u del y, that multiplied with mu is the wall shear stress. So, now let us say so this after evaluation will give a numerical value, say a some number. So, you can write 3 mu u infinity by 2 delta rho u infinity square is equal to a d delta dx. Okay. That means you can now cancel one u infinity, mu by rho will become nu. So, delta d delta is equal to 3 by 2 by nu by a dx, right. So, if you integrate this, delta square by 2 is equal to 3 by 2 mu by a x plus a constant c. So, what is this constant c? As x tends to 0 plus, delta is tending to 0, that is the edge of the boundary layer. That means c equal to 0. So, you will get from here, so let me utilize this space. You will get delta is equal to delta square is equal to some, there was a u infinity, right, somehow I have not written it. So, 3 there is a with nu, where will be u infinity? Denominator, right, here, right. So, delta square will be 3 nu x by a u infinity. So, delta is square root of 3 by a okay 3 by a into, so you write delta by x. So, it will be this one. So, delta by x, again you see you get back the same thing, delta by x scales with Reynolds number to the power minus half. This 3 by a, if you calculate, it will be 4.64 square root. So, you can check this calculation, go through the algebra and see whether you are getting this 4.64. See, the Blasius solution was delta by x is equal to 5 Reynolds number to the power minus half. In this case it is 4.64, not that bad, considering that this is very approximate, and whatever is this approximation, this will be further less if you calculate the skin friction coefficient and the drag coefficient. That I leave on you as an exercise. The method of skin friction coefficient and drag coefficient calculation is exactly the same as we followed for the similarity solution. The only difference is that now you have to use this velocity profile instead of the velocity profile that we got from the similarity solution, but delta as a function of x is what you get from this, which you plug in here. So that will be the answer to your velocity profile, and hence the skin friction coefficient, the drag coefficient, etc.
Friction coefficient is the LHS in that equation in this tau zero.
The skin friction coefficient will not be
in the very first equation.
Which one?
The very first.
Yes, only half will be there. So the skin friction coefficient, to calculate the skin friction coefficient, you can simply calculate this term, but see, this is tau wall by rho u infinity square, but skin friction coefficient is defined as tau wall by half rho u infinity square. So 2 multiplied by this. So if you integrate this, and now you know u as a u by u infinity as a function of y and x. So you can put here and integrate, you will get the dependence on Reynolds number. So typically you will see that Cfx scales with Reynolds number to the power minus half locally, and CD is scales with Reynolds number to the power minus half based on the length L. The next topic that we will cover for the remaining time of this lecture is a very important concept, that so far we have discussed the growth of boundary layer without the presence of pressure gradient. But what happens if there is boundary layer in presence of pressure gradient? This is a very interesting topic, because if we understand this properly, we will get a clue of the motion of various sports balls and how the boundary layer growth affects their motion. So imagine that there is a sphere or a cylinder, whatever, and there is a free stream with u infinity falling on this object. So what happens to the streamlines? The streamlines which are far away from the cylinder or sphere will not understand the effect of this. So that far streamline will be straight and parallel to this. So with respect to this as a streamline and the body of the cylinder as a streamline, this region actually represents a converging flow passage. Because it is a converging flow passage, the area of the flow is decreasing and you have the fluid velocity accelerating. What is accelerating the flow? It is a driving pressure gradient that is accelerating the flow, because if you imagine the far stream, it is outside the boundary layer, so viscous effects are not important. So it is a driving pressure gradient that is actually accelerating the flow. So that pressure gradient which is active till this is called as favorable pressure gradient, because it is favorable to driving the flow. So, favorable pressure gradient which is given by dp dx less than 0. So, that is on this side. On the other side, that is between these two lines, the flow passage is diverging. So, when the flow passage is diverging, the velocity is anyway reducing because of this. So, there is a decelerating effect, and that decelerating effect is due to a pressure gradient which is slowing the fluid down. This is called as adverse pressure gradient. So, in this region, the difference between these two regions is that in this region the fluid will anyway accelerate in the outer stream. In the inner stream it will be slowed down by viscosity, but the favorable pressure gradient outside the boundary layer will try to drag the fluid. So, there will be a monotonous growth of the boundary layer. However, in this region what happens? In this region, let us consider a location like this. The acceleration of the inertia of the fluid which the fluid gained here will still try to drive the fluid. The pressure gradient is opposing the fluid in the bulk, and at the wall the viscous effect is also opposing the fluid. So, the poor fluid which only has its inertia to support, but pressure gradient is opposing it, viscous force at the wall is also opposing it, and it comes to a condition that this fluid cannot sustain its forward momentum anymore. So, when the fluid cannot sustain its forward momentum anymore, there can be a local backflow. So, if there is a local backflow close to the wall, we say that the boundary layer has separated, because this point is artificially a point of 0 velocity. So, as if the solid boundary has shifted to this to make sure that there is a monotonic growth in the boundary layer. Actually, there is no monotonic growth in this region, and there is a low pressure region that is created at the back of this after boundary layer separation. As I told earlier that because here there is boundary layer separation, boundary layer theory cannot be used, because there is no monotonous growth of boundary layer. So, for boundary layer separation adverse pressure gradient is required, but adverse pressure gradient does not necessarily mean that there will be boundary layer separation. So, adverse pressure gradient is a necessary condition for boundary layer separation, but not a sufficient condition, because despite having adverse pressure gradient the fluid might be still having some inertia to maintain the forward motion. But having adverse pressure gradient is a necessary condition, without that boundary layer separation will not take place. So, with this physical understanding of the role of the adverse pressure gradient, so when the boundary layer has separated or got detached from the wall, the consequence is that in this region there is a low pressure and on this region there is a high pressure, because there is a driving pressure gradient, and because of this there is a pressure distribution across the body which is now no more symmetric, and because of this pressure distribution there is a drag force. This drag force is called as form drag or pressure drag. Why this is called as form drag or pressure drag is because this depends on the geometric form of the body and it is a function of the pressure distribution on the body. That is why the name form drag or pressure drag. So, we have learned by this time two important sources of drag forces. One is skin friction drag another is form drag or pressure drag. Net drag is a resultant consequence of this. This is due to tangential force, this is due to normal force. So, how do you consider the drag force? So, whatever is the resultant force distribution, the component of that force in the direction of the flow is called as drag force. So, that component, a part will be due to skin friction and a part will be due to form drag or pressure drag. Now, what we will try to do is, we will try to draw the velocity profiles, the velocity gradient profiles and the second derivative of velocity for the cases of dp dx less than 0 and dp dx greater than 0, assuming that in both cases for dp dx less than 0 anyway there will be no boundary layer separation. For dp dx greater than 0 we will assume that it is still such that boundary layer separation has not occurred. So, what we will do is we will make a plot of okay. So, this case we will plot for dp dx less than 0 and this will plot as dp dx greater than 0. See, despite having books we have to go through classes and I will show why, because this diagram we will draw not starting from the left to the right but from right to the left and we will build up the diagram. In the book when the entire diagram is drawn, it is very difficult for students to follow that what is the sequence, logical sequence in which the diagrams are arrived at. So, we will start with the second derivative. So, write the boundary layer equation at the wall. Now, there is a minus dp dx term. So, at the wall u wall is 0 and v wall is 0. So, at the wall d2u dy2 is equal to 1 by nu dp dx, right. So, if dp dx is negative, which is favorable, then d2u dy2 is negative at the wall. So, something like this. What happens to d2u dy2 at far stream? d2u dy2 is what? d dy of du dy, du dy, so d dy of du dy, partial derivative of course, but conceptually it is okay. So, del u del y decreases with y, increase in y, right, because it has to be 0 at the far stream. So, this is negative in the far stream. So, you will have d2u dy2 diagram like this. What is du dy? So, here there is no boundary layer separation. So, tau wall So, tau wall will be positive and du dy will be positive and du dy will be tending to 0 as you go to infinity, and u versus y will be the usual. More interesting case is this. So, at the wall, if dp dx is greater than 0, then what is d2u dy2? It is positive. Far from the wall, d2u dy2 has to be negative. So, it is asymptotically 0 somewhere. So, it is negative far from the wall, positive here, that means because it is continuous it must have somewhere crossed the y axis, right. Okay. So, this means that there is a point at which d2u dy2 is 0. At the wall it is positive, at the far stream it is negative, it is continuous, so somewhere it must cross the 0. Where d2u dy2 is 0, there du dy must be maximum. So, you can have a du dy plot like this, and where du dy is maximum, you will have a point of inflection in the velocity profile. This is called as point of inflection. So, this point of inflection is a hallmark of the possibility of boundary layer separation. So, by physically looking at the velocity profile, if you can identify a point of inflection, then you may sense that there could be a possibility of boundary layer separation. So, to summarize, we have discussed the boundary layer in presence of pressure gradient, in the absence of pressure gradient to begin with, and now in the presence of pressure gradient. We have identified that there are two types of drag forces, skin friction drag and form drag and pressure drag. Question remains that for different types of flows how these drag forces vary. For example, if the flow is not laminar but turbulent, then how this drag force will change. We will discuss that when we have completed a little bit of discussion on what is turbulence and some introduction to turbulent flows, and then we will come back to this point and discuss that if you have a turbulent flow instead of a laminar flow, how the drag force distribution changes and how that can influence an engineering device and even motion of cricket balls or tennis balls. Thank you very much.